Yeah, so the second lecture took a little longer than I hoped. However, some of you spent another hour with me going through some of the details, so I, as I said, share the calculation we did, clarified a few things. Now, okay, so it's, I'd like to say a few things today. I suspect we're going to run out of time again, but it's good to be ambitious in the beginning. So I'd like to talk a little bit about, okay, so let's recap our progression so far of ideas. We started by motivating why we're studying this problem, then we discussed the classical problem and its features, and we studied the classical problem first at the level of a classical field propagating in this space, and then we considered small perturbations of the geometry itself, which is a natural question to ask at the classical level. And then we turned on a small h bar again, starting by sorting out sort of how the operators behave at late times, what's the appropriate operator algebra, what are these symmetries, what is unitarity from the perspective of representation theory. And we understood that in terms of these alphas and alpha plus and alpha minuses, and we understood a little bit of the classical physics in terms of the quantum fields. Quantum fields late times in de Sitter. And then I discussed briefly, and I apologize for the contour, I had a minus sign in my head that was wrong. It had to go completely the other way. It had to start in the slightly negative and go up. And then we discussed the construction of a wave function that is de Sitter invariant at tree level at least, and probably at loop level at very late times, and some of its features. Now, what I'd like to do today is try. We're going to be a little bit more, dangerous and try to think about geometry itself. But of course, to play it safe, in the beginning we'll think about geometry in the semi-classical limit, which means we will think about tree-level effects. So the wave function of geometry at a tree-level approximation. So that means we can have large field configurations away from de Sitter, but always consider the tree-level contribution to that. Now, the idea, this is a tricky business, the idea that there should be some description of a quantum state in terms of a geometry is extremely tricky. At some level, it may well be wrong because it assumes that the fundamental degree of freedom that's being quantized is the geometry itself, and we have reason to believe that that might not be the case. And indeed, when we explore some more concrete models, we'll see that there is a sense in which that's not the case. However, in a semi-classical limit, it seems to be an appropriate thing to do. And so the idea, which stems from Wheeler and DeWitt, the idea was let us assign a wave function to a 3 metric, okay, on some slice. Now, gravity is a gauge theory, and in being a gauge theory, the wave function has to be subject to constraints that arise due to the gauge redundancies. And so the wave function of Wheeler and DeWitt indeed is a wave function of 3 configuration. However, it has to be annihilated by the generators of the 4 diffeomorphisms, okay? And what that means effectively is that there's a reparametrization of the slice. So one imagines splitting space and time into slices determined by some induced metric along the slice, and time determined by some shift, some vector that tells us how we move along, right, this time. And we have to be invariant under reparametrizations on the coordinates on each of these slices, as well as changes in the clocks that tell us how we evolve from one slice to the next. And so one of these has to do with time reparametrizations, and so what ends up being the case is that the effective Hamiltonian of the theory essentially annihilates the state. The Hamiltonian generates translations in time. If time is itself a gauge redundancy, in the absence of any boundaries, where we might define charges asymptotically by switching off the gravitational field, we are left with a constraint equation, which is that the Hamiltonian of the canonical gravitational action annihilates the wave function. And this simply means that whatever slice we choose, they should be physically equivalent. And the other one is simpler to imagine. It's simply the statement that the wave function has to be a coordinate invariant functional of the induced metric along the slice. Now, I'd like to talk about these constraints not generically, so they're true for any sort of Lagrangian that has the Einstein theory, but I'd like to talk about them in a limit where the size, the proper volume of our slice becomes arbitrarily large because they simplify. And we don't need to complicate our lives too much. And since this is where we've been studying the geometry all along, I'd like to stick there. Now, a nice reference that discusses this point is this paper over here. I find it clearly written. So now let me simply state the constraints. Pimentel. Yeah. So now let me simply state the constraints. And let's remember the data roughly. So recall that if we allowed these large fluctuations, I shouldn't call them fluctuations, large geometrical deviations, our data was organized in terms of this 3 metric over here, and then there was an ongoing expansion in small eta. And so the natural object that our wave function will be a function of is this 3 metric over here. And notice that we're again in the limit where eta goes to 0. And so the proper volume of this object is actually scaling up. Okay? And so so now we imagine that we have functionals, non-local in general, functionals of this 3 geometry, and we'd like to understand what constraints they have to satisfy in order for them to be part of the Wheeler-DeWitt Hilbert space. Okay? And so one of them we can sort of guess. It's that basically under a tangential coordinate transformation by some spatial 3-vector psi, the wave function remains unchanged. In other words, if I choose a different coordinate system to describe G0, the wave function as an argument of the transformed metric should be equivalent to the original one, right? This is simply the rule that you can measure things how you wish, distances, lengths, but the state when that is a gauge redundancy of your theory should be independent. Now, the other condition, which is usually a trickier condition in standard, yeah. Oh, for general gauge transformations, you do a general diffeomorphism on the 3 metric. Oh, sorry, you mean in the sense of boundaries. I'm assuming that the Cauchy surface is compact in this analysis. Yeah, so we're not going to concern ourselves with those things. So okay, that's an important point that's making. Of course, if our space has a boundary, let me just mention it. Since we're accustomed to this situation oftentimes, if our space does have an asymptotic boundary where we can switch off the gravitational field, it could be the case that certain diffeomorphisms are large enough near the boundary that they change the canonical data and hence the state. So this is not the situation we're in because we will assume that we have a sphere or something, so there's no boundary to place such a boundary term, and we will have smooth but large possible vector fields living on this sphere. Okay, very good remark. So the next constraint, let me make put it into context. So typically, this is considered the complicated constraint in the context of Wheeler-DeWitt theory, because the operator that annihilates the wave function is quadratic in the momenta, and it's not a nice and simple relation, and it's generally hard to solve. And people have to resort into what was called the mini superspace approximation in order to get some intuition about the equation. The mini superspace approximation was an approximation where one threw out essentially all the degrees of freedom in the 3 geometry except one parameter, perhaps the size, and studied that complicated equation as a function of that size. This was a very aggressive approximation, however, it was for a long time what people sort of could control. Now, something nice happens in the limit of a very large proper volume, which is that that constraint simplifies dramatically to a constraint that can be stated clearly, and it's the statement that the three geometry, oh, and again, I'm working in 4 dimensions. Okay, the three geometry, the wave function is a function, the three geometry should be invariant under local Weyl transformations of G0 itself. Okay, so it should be insensitive to whether we are discussing the geometry G0 or whether we are multiplying it point-wise at different points by different Weyl factors and considering that geometry. In other words, this is a conformally invariant functional of G0. And you should view this roughly as what I was talking about before, which are the slice reparameterizations. Because if I define my clock locally at every point by some other clock, okay, but scale up, what happens is that you effectively multiply G0 by your now space-dependent clock. And there's an auxiliary diffeomorphism you can do to absorb the other terms that are produced at the same level, for example, the G8-8 or G8X terms. If you have other fields at late enough times, remember all of this structure was acquired by the other fields, and what you need is a function that's generally conformally invariant under the fields with their appropriate scaling dimensions. So, now, so these are the constraints. These are the Wheeler-DeWitt constraints, and if we find a functional which lives in this class, we're in a good situation, because we could claim that this is a candidate wave function at the semi-classical level for cosmology. So let's ask ourselves the question, but a priori it's not obvious that these equations have solutions. For example, it could have been the case that the Wheeler-DeWitt equation is so complicated that it's an equation for an empty class. Now, the good news is that all of you are familiar with some functionals that we believe as physicists obey these constraints. Any takers? So, so we believe in that if we consider, for example, a local quantum field theory in 3 dimensions, a Euclidean local quantum field theory in 3 dimensions that enjoys conformal symmetries, we believe we can couple such a theory to an arbitrary geometry, and upon doing the path integral, we will end up with a functional of this geometry, which in 3 dimensions, in the absence of Weyl anomalies, is supposed to satisfy such constraints. And so we believe that this is a general class, but just to give you an example, which we'll return to later on, just for fun, let me give you an object that mathematicians also believe exists, and that is, hopefully I'm getting it right, the functional determinant, which is zeta function regularized of the conformal Laplacian on G0. Okay, so this is an object that's sensible and can be studied. It's a functional determinant, and you can ask what is the determinant of this object. It's a highly non-local function of G. So this is a Laplacian on G. However, the Laplacian itself is not conformally invariant, but if you add to it a certain term, which is the Ricci scalar over 8, I believe, in 3 dimensions, then it does become conformally invariant. And the claim is that this, to rigor, satisfies our constraints. So the class is indeed non-empty. This and any function of this, for that matter. Now, however, this is not quite good enough because we need our state to have some additional physical features. If not, we're just dealing with something that could describe anything. For example, this should have sensible probabilities. So what that means, for example, is that there has to be some sense in which this functional is a normalizable function. If not, what are we doing? So, again, before going into the fully fledged notion of a norm for this object, what's an even simpler condition that we might want? So if we imagine that our state is near, in the semi-classical limit, to a pure de Sitter geometry, we would like our state near the metric of a pure, so what's the metric at the boundary of a pure de Sitter geometry? It's a round metric on the three-sphere, or any diff invariant or any Weil invariant metric, okay? So we would like that if we consider small geometric perturbations outside the conformal class of the round metric on the three-sphere, we would like the wave function to be Gaussian suppressed for those fluctuations, right? So this would constitute, at least in some small linearized sense, a quantum state that is fluctuating nearby a semi-classical or classical de Sitter universe, okay? And what does that mean? What it means effectively is that the Gaussian term that we talked about yesterday for these fluctuations has to have a minus sign, and there'll be some kernel, some two-point function, which so happens to be that two-point function of a conserved spin 2 current in 3 dimensions, okay? So it's a two-point function of a 3D stress tensor. So far, all of this follows from the structures and the symmetries, but we would like this to be the case, so at least locally, we know that our quantum state, regardless of what happens at very long times or non-perturbatively, you know, maybe there are barriers, maybe it decays, but at least locally for a long enough time, fluctuations are well described around the saddle, which we believe they should. Now, so, we can go back and ask ourselves, maybe this class is empty. However, this is an object that we have sufficient control over that we can even study for small fluctuations. And indeed, it is Gaussian suppressed, interestingly enough. And so that's nice. It seems to describe some geometries. Yeah. This contraction is in the background de Sitter metric. Yeah, so here I'm assuming it's flat, sorry. So this is a local expression. And really I should do this two-point function of stress tensor on a three-sphere and contract with a round metric on a three-sphere. Okay, good. Yeah, so everything has to be linear in delta G, and so we contract with the background. Now, so as I said, interestingly enough, if you can write this as a e to the trace log, the timeless formula e to the trace log operator, and expand the log, and you will indeed discover upon zeta function regulating that this has this property. So this class of general functionals is also non-empty, good. And but however, of course, at some point we're going to have to confront a more complicated question, which is, given some norm, and this is where things get tricky beyond perturbation theory. What's a sensible norm in the Wheeler-DeWitt theory? And part of the reason it's tricky is that the operator that acts on the states in Wheeler-DeWitt theory is not generally positive definite. So it's an unusual Schrodinger equation in that it looks like a Klein-Gordon equation. But I don't want to confuse you with that right now because we're going to take a different approach. However, if there was a norm, it would have to satisfy certain features. For example, it would have to be Weil cross diff invariant. The measure that we integrate over G0 should be Weil cross diff invariant. So we have to divide by the volume of the gauge redundancies that we integrate over. And for example, we could imagine squaring this object and calculating the expectation value of some Weil cross diff invariant observable. Yeah. Mm-hmm.
Do you think it has this form, plus?
Yeah.
That's the statement.
That is the statement.
And plus higher order term.
Correct. You know this statement very well because this is the partition function of a free theory with flipped statistics. And so the stress tensor has the wrong sign two-point function, which gives you the correct Gaussian suppression. And there are also three-point functions for the stress tensor in a free theory. And so you're going to get all of these terms here as well. So what do you want to do?
There's the usual definition of the norm in geometric quantization, which is you look at a set of all classical solutions, and then there's a definition.
You're assuming you know the symplectic form on the phase space.
You know the symplectic form because you have the initial action. The action is right there. So you know the symplectic form. Why is that not a, why is that not the natural guess?
Right, so this is a system with constraints, and so you have to take those into account.
Yeah, the good thing about classical solutions, by the way, is all this happens automatically. Right? So if you take a set of classical solutions, then you automatically have a set of classes.
Classical solutions.
Which are parameterized by distribution.
Yeah. That's this norm.
Yeah, so I'm not sure what I've never actually seen anyone work out what the expression of the norm would be in terms of the metric. It should be some answer, but I don't know what they're asking.
That's this norm over here, I think.
What does that norm say?
Well, the Val cross. Yeah. I'm trying to remember if I have a reference in mind. I do, but let's not go there. So the only point I wanted to measure is the only point I wanted to mention is that the Wheeler-DeWitt operator is like the Klein-Gordon operator, and so there's subtleties in quantizing a wave function that looks like the Klein-Gordon operator. Now, the gauge redundancy comes into play because the negative direction has to do with a particular piece of the 3 geometry, which is the scaling part of the geometry, and so you might decide to gauge fix in such a way that that's not an argument in your wave function.
So in DeWitt's original paper, he tried to write down a metric in space of I know in DeWitt's original paper, he wrote down a track called thing and then he defined a norm by defining.
He just did a canonical analysis, right?
Yeah, but the norm he guessed. He guessed the norm by writing down what metric.
Yeah, so I'm not sure. Yeah, right. So the norm, I think, is an unsettled business. Maybe your proposal is correct. However, it doesn't seem to be a settled business. And the issue, again, is that the Schrodinger operator has indefinite sign. And so if you quantize this, you're starting from a classical analysis to get the Schrodinger operator, right? You identify your canonical momentum, your canonical position, and you end up with an operator that doesn't look like a positive definite object acting on psi. That's constrained, right. So if you take the gauge symmetries into account, indeed one of these negative directions could be gauge fixed in an appropriate way. But again, this is a limit where I find it a little less ambiguous because at least you've decided unambiguously what that slice is, right? If not, there might always be the ambiguity of why you picked one slice versus another. So I think in this limit, this is a slightly less ambiguous question, which is why I like thinking about the problem in this limit. Okay, good. So any other questions? So far, we've talked about general structure, and I think at this point, it will be useful to try and see many of the features we talked about in some concrete setup, okay? So far we've given a general picture of what it could look like and what the constraints are and all that. And so I'd like to at least mention a few features of a model where we can study these objects in detail. But before doing that, I think it's instructive to pause and collect the differences that we've observed so far between conformal field theory and conformal symmetries in anti-de Sitter space and what we're seeing in de Sitter, okay? So the first thing we observed that was different is that each field in the bulk, so now I'm briefly going to talk about in a language that's ADS CFT-like, just to make the comparison. Each field in the bulk of de Sitter, at least perturbatively in a linearized sense, corresponded to two conformal operators, not one, okay? In ADS, each quantum field in the bulk corresponds at the boundary to a single conformal operator, okay? Related to this, the conformal data that we labeled our operators with respect to and organized our states with respect to in de Sitter corresponded to unitary reducible representations of the Euclidean conformal group. So even though it's a Euclidean group, we realize that unitarity of this group is the unitarity relevant, at least in the limit of perturbative physics, for an analysis in de Sitter. In ADS, we have to obey the rules of unitarity for the Lorentzian conformal group, okay? And those, as we discussed, are vastly different. So here we get a collection of highest weight representations. Essentially everything transforms under those. There's unitarity bounds on how low the weight can go. The weight has to be real. OPE coefficients have to be positive. And so that's another important difference. Another difference is the role of locality on the late-time surface. So in ADS, we expect that the dual description is given by a local conformal quantum field theory, and so the role of locality is extremely important in understanding the system. In de Sitter, the role of locality at late times is far more questionable. If we have a process that occurs at early times, it will generally affect non-local regions of the late time slice. There's no reason why we should organize our thoughts about quantum field theory at the late time surface in terms of local insertions of operators. In fact, if we act on the quantum state with a local insertion of an operator, because the Hermitian conjugation retains the operator in its original position, the inner product will be rather singular. And so those aren't nice states in the Hilbert space. In fact, nicer states would be somewhat smeared actions of operators in the late time slice. So the role of locality is suspicious in de Sitter, and this is related to the fact, well, it becomes even more clear when we realize, like Spanda was suggesting, that ADS having a boundary allows for a global symmetry group, okay? It allows for conserved charges. It allows for conserved quantities to be defined, whereas at least for compact Cauchy surfaces, there are no global symmetries in the gravitational de Sitter theory. The de Sitter group is a subgroup of the group of diffeomorphisms, and so it has to be gauged away. So if semi-classical gravity gives us any hints, any sensible observable has to be also SO4, 1 invariant, and not just diff invariant, but transforming under the de Sitter group. Okay, so this is something we would rarely do in ADS, and the reason it would be hard to do in ADS is that typically there's a unique SO4, there's a unique conformally invariant ground state in Lorentzian conformal field theory, whereas, as we said before, given the fact that now we have representations not just with the weight, but also with the shadow conformal weight, and we can consider transforms of operators, there's ways to glue operators together and create potentially a plethora of de Sitter invariant states. And so there's no unique de Sitter invariant ground state that is no longer the single principle that determines a special state in the theory. We have to think harder to associate a special state in the theory, or maybe there isn't one. Okay, so there could be possible de Sitter invariant vacua. And that better be the case because we just argued that our observables have to be de Sitter invariant. And so if we have de Sitter invariant observables acting on a de Sitter invariant vacuum non-trivial, it's going to create a new state, which is itself DS invariant. And so we're starting now to get a sense of the differences between these two problems that at a very naive level might look almost identical. Like it's more than just a minus sign, is the point I'm trying to make. So for example, if we're interested in using the power of something like the bootstrap, the conformal bootstrap to solve theories in de Sitter, we would really have to essentially change all the rules that go into the program, all of them. And we would have to confront things like continuous sets of conformal dimensions. Because in the principal series, for example, it was 3/2 of psi nu, where nu was any real number. And if you fuse two operators together in de Sitter, you will generally get an integral over all of these things, okay? So the 4-point function of fields in de Sitter may well be expressed in terms of an explosion of operators, a continuum of operators, and it's not clear whether that's the nicest organization of the problem anymore, okay? Sorry, what? I'm doing what?
Let's say you wanted to use the bootstrap. Even if you could use it in that dimension, you do not say you're talking only about the coefficients that appear in the expression. Because you don't have locality.
Yeah, so what I'm imagining is starting with the pre-Hilbert space, something that isn't a set of normalizable states in the Hilbert space, which are these local insertions. These are operators in the theory. Well, what I expect, given that there are known SO4 functions on the space of SO4, 1, have a completeness relation. They have an expansion in terms of blocks. One can do that. This is a complete functional basis. And so there's a sense in which you could imagine trying to expand 4-point functions in terms of the conformal blocks of the SO4, 1 invariant data, and try to interpret it in terms of de Sitter. However, I think it might be a challenging task. So if a 4-point function in de Sitter will obey the Ward identities of conformal field theory, right? Right. No, the physical 4-point function. De Sitter expectation values. Let's talk about quantum field theory in de Sitter. Obey the de Sitter, the conformal Ward identity. But let's go back a second first. So we're asking, okay, let's even see whether for quantum field theory, this approach is good. It might be good, but it'll be very different. And I want to emphasize the difference. Now, when you allow gravity to fluctuate, we have to be careful, and I think the best approach will be to try to study a model or whatever, try to find another handle to control the problem, right?
All these things that you have enumerated in the de Sitter column.
Yeah.
Most of it will also be true for flat space.
Flat space has its own subtleties because it has a null boundary, and there we think the problem might nicely be organized in terms of the scattering amplitude data, and I think maybe that's the way to think about the problem. Over here, you see, and in flat space you don't have the conformal group, or you do in a more subtle way. You have the Poincaré group, but there's an SO3, 1 that looks like the 2D conformal group that transforms the sphere at null infinity in nice ways, and again, these representations should and do show up there as well, if you carefully think about the problem. However, flat space is sufficiently different that we don't get too confused about ADS. We don't try to compare it to ADS instinctively. In de Sitter, we really have to sort of separate the two problems. Yeah. Correct, yeah. Yeah, so if the sitter is eternal, okay, this will be my closing remarks. So let's leave it for there, because I want to get there, and I'm sensing my electronic clock is not working today, but I'm sensing that time is running out. My classical clock is okay. So okay, let me at least mention a few things, and then afterwards we can talk about it. But I want to at least mention some features that came from two papers, and the period between the two papers is 6 years, and that doesn't indicate that there was an absence of thought in those 6 years. It was just there was a paper written here with Hartmann and Strominger where we proposed an interesting direction that might be useful to think about the sitter, but it looked at least you know, the authors of this paper, so Denef, Monten, Sun, and myself, 6 years to understand what the hell we were talking about in 2011. And so, so these are two papers that are concerned with the question of interacting massless higher spin particles in a de Sitter universe. And so now let me make a brief remark about the final representations that I talked about. So if you remember, I said that for sort of large spins, the irreps came in finite sets with a depth parameter, which was discrete, that went from 0 to s minus 1. And so if they're higher spin particles in de Sitter, they have to be organized in terms of these irreducible representations. And so let's start again with our logic. I'll just mention the results, given my time constraints. So at very high mass, higher spin particles in de Sitter transform under the principal series once again, okay? Now, as one lowers the mass, something interesting happens. What happens is that at a finite but non-vanishing mass, known as the Higuchi bound, so it's a mass of order the spin, okay? What happens is that one encounters a bound where if one goes below that bound, some of the polarizations of the massive higher spin particle acquire a negative, a wrong sign kinetic term, okay? A negative norm. However, as was later discussed by Deser and collaborators, it was realized that if you continue, I think that it was realized by Deser and collaborators, that if you continue going down, but before hitting the masses point, you will hit a certain special discretion of masses for which these negative norm states become pure gauge of a reduced gauge redundancy that only happens in a de Sitter type of situation. And so what was realized is that the higher spin particles in de Sitter have something interesting. You tune their mass as a function of the de Sitter length, they hit this Higuchi bound, and then they become non-unitary, and then they become unitary at very special values. And the number of values for which they became unitary again was s minus 1. And and of course it's completely aligned with unitary reducible representations of the de Sitter group. These are the discrete series of Harishchandra, and secretly it was known to them all along. And at those points, the conformal weights that label the late time operators alpha plus and alpha minus are indeed integers, okay? And so this discretum over here, from the de Sitter point of view, has to do with acquiring certain structure as our weights become integers. And when t is equal to s minus 1, so just to give you the general formula, delta was 2 plus t, delta becomes s plus 1, or shadow weight. And of course, that's the dimension of a conserved current, and that is indeed a massless particle in de Sitter. So a photon, a graviton, and massless gauged higher spin particles in de Sitter transform under these representations, the maximal depth discrete series representations, okay? Now, an interesting comment about string theory. So string theory is a theory with higher spin particles, which have a lot of mass, and we tend to think we can tune the mass of these particles by tuning the length of the string, for example, in terms of some length scale of your target space. And this is some marginal deformation of the worldsheet theory. So if there is a perturbative string in a de Sitter universe, at some point, you have to see this structure, right? And that's not the point. Like in ADS, you can tune this all the way until the particles become massless. In de Sitter, you start acquiring these special points. And this should manage, if there exists a perturbative region of string theory where de Sitter universe exists, and there exists a knob in the worldsheet that changes the mass of de Sitter, this has to be a feature of the theory. Okay. So now we're going to talk about a theory, which let me discuss it's the good news first. It's a theory that lives in four space-time dimensions, and it has in its spectrum a scalar field whose mass is in de Sitter units +2. It lives in the complementary series representation, but it has positive mass, and it's the only scalar particle in the theory, so no tachyons. And then we have particles that correspond to every massless field allowed. Okay, so you have a photon, a graviton, a mass of spin 3, spin 4, spin 5. So the additional spectrum that we've added to the theory is what allows us to control the theory mathematically. So the good news is that theories with this spectrum have been studied, and the classical equations of motion of these theories, so something analogous to the Einstein equation, if we just did a spin 2 particle, were written down in work by Vasiliev. Okay, he wrote down an equation that was nonlinear in these fields, that was invariant under all of the gauge symmetries, the nonlinearization of the abelianized gauge symmetries, and it's a very rich and interacting classical system of higher spin massless waves. And the nice thing about these theories is that they admit both there exists Vasiliev theories that live that have a classical vacuum, which is anti-de Sitter space, but there also exist theories in Vasiliev that have classical four-dimensional de Sitter vacua. Okay, so at the classical level, both of these theories exist, just like Einstein gravity with a positive cosmological or a negative cosmological exists. There's a choice of sign you can make that retains the positivity of the quadratic terms of all these particles, and so at face value, these two theories exist, and moreover, the de Sitter theory, which we will focus on today, admits at the nonlinear level a solution where all higher spin fields are switched off except the metric itself, which is given by four-dimensional de Sitter. So this is an interesting situation because, as was discovered by Vasiliev and collaborators, these theories have an infinite dimensional symmetry. So these theories are very constrained, so much so that all of the coefficients in the theories are constrained, except the overall coefficient of the action, which is you can view as the size of the de Sitter universe in Planck units, and and this symmetry, for the more mathematically oriented of you, is known as a universal enveloping algebra of the conformal group. But for the rest of us, this is just the group of symmetries of a free scalar field in three Euclidean dimensions. Okay, so there are a lot of fields, and this led in the ADS context Polyakov and Klebanov to suggest, at least for the simplest theories, that these theories were related to models that had a vector-like structure in the large N limit. And so one is prompted, given the observation that these theories exist in de Sitter as well, one is prompted to study as mathematical toy models, the properties of these theories, which is what we set out to do in that work. And we found, so the discussion happens in two different contexts. One was a Wheeler-DeWitt type approach, where the challenge was to write down a wave function, much like the one we discussed, whose argument now was everything. So write down the Bunch-Davies wave function for the full collection of late-time profiles of higher spin fields. Okay, so this was one result that was obtained, and it's not the result I want to focus here, but let me just mention that this can be packaged rather nicely in a functional determinant type of situation, where bxy is, you should view as a bilocal function which admits a Taylor expansion when y tends to x, whose coefficients are functions of x, and they're the profiles of all the higher spin particles. So this is the analog of the semi-classical wave function, Bunch-Davies wave function of Vasiliev the universe, that encodes all of the perturbations of all the particles. And one thing to observe, going back to Suvrat's comment, is that it indeed encodes a lot of interactions, right? So the fact that that functional determinant I talked about before had cubic, quartic, is the fact that the bulk, that quantum state in the bulk produces a lot of rich infrared physics at late times. And so it's an extremely rich cosmological wave function, even if viewed sort of as an object, even as a wave function in and of itself, and one can study its features. And it's positive here because of the Gaussian suppression, you see. This was the comment I made before. It has no reason to have a minus sign, because we're only talking, here we were looking for a functional that has some features. And so the conjecture, which can be checked, thanks to work of Jombi and Yin, can be checked at the cubic level for all particles in de Sitter. The sign is fixed by the Gaussian terms, and so it really is the wave function of the semi-classical Vasiliev theory. Far, far, far beyond any mini superspace approximation, if the conjecture is correct. And so this is an example of a true sort of semi-classical object that satisfies the symmetries, and we believe is the natural sort of Bunch-Davies state of this universe. However, when confronted with the question of sort of what's the right measure, is it even sensible to talk about psi squared and inner products, one is led into several more problematic issues. And the reason that this is a little more problematic is that there was no principle at this point as to how to integrate over this space of configuration. What was the range of B's? Within B is the metric. Typically, we impose that the metric is positive definite. So we couldn't just freely integrate over all the BXYs as if they were flat or free parameters. And so we didn't have an answer to this question. And so, and I believe the reason this was a hard question to ask is that it was the wrong question to ask. Ultimately, for similar reasons to those in any gravity theory, trying to continue with this approach was essentially assuming that the correct microscopic degrees of freedom of the theory were the higher spin fields themselves. But this is a classical theory, and these profiles are effective fields. And so we ended up, however, at large N, this gives us an important amount of data to compare to any proposal for a microscopic theory. Now, it seems I'm running out of time, but so conjecture number one was this realization that these theories are rich, interacting, and admit de Sitter vacuum, and we can write an expression, a Wheeler-DeWitt wave function for these theories. These are these bilocals that Javicki and Das like to work with, and yeah. We know how to integrate over them when we know where we came from. So, in free field theory, we know the Jacobian because we started with the vector fields and then did the field transformation. Here, but your intuition is correct. Here, I just declared this to be the case. And precisely that intuition should be right in the de Sitter context as well. And that's the suspicion. And so, however, it has to be an intuition that also works with all of our other constraints about de Sitter. And so the action is not known for these theories, and so we don't have access to the symplectic structure. This is part of the issue. This is why the measure is a hard thing to get. So, however, Vasiliev theory doesn't have an action. So it's like if you have just the equations of motion, it's not quite enough. If I give you a function psi of x, you don't know how to calculate probabilities. If I tell you that p comma x is equal to I, you know how to calculate probabilities. So this was part of the issue, that just the wave function is not enough. So, yeah, well, this is conjecture number two. So conjecture number two is precisely that. And the intuition is that of Spenta, that these must not be, whatever the true norm, whatever the way to calculate probability, if there is a way to calculate probabilities in this theory, it has to be with respect to the appropriate degrees of freedom. Or at least in those degrees of freedom, it should be the flat measure. You see? Just like in the ON model. Now, the claim is as follows. So we used a trick. We used the observation that we made when we were constructing the Bunch-Davies state, that it is in a natural way related to analytic continuation to ADS Witten diagrams, at least at tree level. And so in knowing that, and in knowing the conjecture of Klebanov and Polyakov, there was enough information to construct a reasonable conjecture, essentially if one is true, so is the other, for the wave function itself. Because that was the object that was most naturally connected to the calculations in ADS. But it left open the question of how to integrate over it and all that. So this was the justification of that part. Now, in this later work, we made the following proposal, and let me just Okay, let me just state the proposal, and then people can stay. Okay. So, and I'm going to make a statement about how to compute, how to generate not all the pieces of the wave function, but rather the correlation functions within the physical state at late times of de Sitter. So the claim is as follows. We begin with a collection of operators. So just view these things as definitions for now, right? So as a set of definitions, so I goes from 1 to n, x is a point on R3, on a box, and we have an operator algebra, which is just q, comma pi, standard fixed operator algebra. And out of these operators, we're going to and notice that, so we have 2n operators at each point. We're already sort of doing something different from ADS. So there's a Hilbert space, there are these operators that act non-trivially on them, and there is a non-trivial operator algebra as well in terms of the q's and the pi's. And now we're going to build a collection of composite operators. which are given by taking these Q's, contracting the index I, which runs from 1 to n, and inserting between them these derivatives that appear when you build conserved currents in free theory for each spin. Okay? So we have a collection of composite operators now. And finally, I'm going to tell you a state. Yeah. In 3 dimensions, in lower dimensions, it would. So the analog of that is this this enormous higher spin algebra. So we'll get there. Yeah. Very good. Okay. So. Okay. And so now the other thing I want to tell you is I'm going to tell you a particular wave function, a particular quantum state. And this quantum state I'm going to express in the eigenbasis of Q operators. I can do that. They commute amongst themselves. And it will be given by a Gaussian object, a Gaussian wave function with 2 Q's and a Laplacian inserted between them. Some quantum state in our theory. Okay? So what have I done? So depending on your taste, I've defined a quantum theory for you, or I haven't. Because though I've given you an operator algebra and a Hilbert space, I haven't declared a Hamiltonian, and I won't. What I've given you is a collection of operators that act on states, and I've selected a state which is nice in that it's Gaussian, it's free, and in that it's invariant under all the symmetries of Vasiliev's theory. Okay? So now we can make, so now we've built our definitions, and now we can make our proposal, which is that yeah. These are just operators in my theory. I will now interpret them. I haven't put any canonical momentum yet, but of course I could consider, very good, and this is something unusual from the point of view of Euclidean theory, but of course I could also consider such operators. After all, they're invariant under the ON symmetries, and indeed we'll see that they play an important role. These operators don't commute with these operators amongst themselves. Yes. Well, QP, P's commute amongst themselves, Q's commute amongst themselves, Q and P don't. Now, these maybe don't, I'm not sure. I think at large n they do, and then you have to correct them with one-over n corrections to retain the fact that they commute. This will be an extremely important point in a second. No, H's commute, because they're built just out of the Q's and the Q's commute. It's these guys that are built out of the Q's and the pi's whose algebra might be more involved. But at large n, I believe they commute. Now, sorry? Yeah, so one would have also pi operators. Yeah. So I'm about to do that. So now let's make a proposal. So I just gave a definition, some operators, and these operators, I should say, from the perspective of this wave function, they transform under the conformal group, and they transform as delta equal to 1/2 spin equals 0 objects. And now we can, for example, ask ourselves, the Q's transform, well, so let me make the statement and then, So now I'm going to make a statement, which is that the late time profiles of the slow falling modes of the higher spin fields, these are operators, remember, in de Sitter, are these operators themselves. Okay? And the Bunch-Davies state in Vasiliev is this Gaussian state. And so I've given you a recipe to calculate all of the correlation functions now with the measure, right? Because the measure is just a flat measure in terms of the Q's. For these H of Q's inserted at different points. So this is a calculation that hadn't been done in Vasiliev because we were studying the wave function, but it's a calculation you could ask about. What are the cosmological expectation values of all the higher spin fields in Vasiliev? And if the theory has a quantization, this is a sensible question to ask. And so the claim is that, so at late times, these calculations will be organized in terms of these alpha pluses and alpha minuses. And the alpha pluses, the slow falling ones, we claim are these operators over here. And the conjugate momenta, remember that alpha plus and alpha minus had a non-trivial Heisenberg algebra, are built out of these and the pi-pi type operators. Okay? But one cannot satisfy the Heisenberg algebra exactly because of the non-trivial commutation relations between Q and pi. You see, in the naive picture of Vasiliev, at each point you have an infinite tower of higher spin degrees of freedom. But in this operator, in this theory, at each point in space, we only have n degrees of freedom. So we have a vast reduction in the number of operators in the theory. And so one cannot conceivably satisfy at each point in space the Heisenberg algebra for an infinite tower of independent higher spin operators. But what one can do, given a proposal for the profiles, is try to get as close as one can in the large n limit. And this is, and so part of the story is a construction of the alpha minuses given the alpha pluses when they're built out of these fundamental degrees of freedom. Now, the other good news about the large n limit is that these calculations over here, which we can do, for example, for 3 and 4 point functions explicitly, at tree level can be compared to our original wave function picture, where to leading order in large n, one may assume that the details of the measure are inconsequential, right? For low enough correlation functions, one can compare these to a naive calculation in the theory whose argument was the full set of higher spin fields, and at least to leading order in n, where the effects of the measure one hopes are inconsequential, the two pictures agree for all correlation functions of all higher spin fields. Okay, so the semi-classical agreement between our more fundamental microscopic operator algebra and quantum state, and what we believe is the appropriate Wheeler-DeWitt Bunch-Davies state and sort of canonical configuration space in the semi-classical theory. Now, yeah.
At this point, you're not proposing
Not yet, not yet. You guys are fast, which is a good thing right now. So now so we're going through our list, one by one. Now that we're all prepared, we're going through our list. And so now we can ask precisely that question, because we know what the full symmetry of the theory is, right? And so it's not only ON invariant operators that we might be interested in, it's also higher spin invariant. Given that in these theories, what replaces the de Sitter group is the higher spin group, we have to gauge the full higher spin group if we follow the logic that we followed up to now. So how does the higher spin group act on these Qs? So of course there's a ON transformation that acts on this index in a simple way. Okay, that's fine. But it turns out, and let me give you a schematic derivation of why. So remember, if you have a free scalar in 3 dimensions, the Euclidean action is just given by phi Laplacian phi. And now, remembering that locality is not no longer the boss, let's consider general linear transformations of the field onto some other field configuration. So let's take another bilocal, u of x comma y, integrated over all y with a field at y, and produce a transformed field. And let's ask, for this general class of transformations, which ones leave this action invariant? And the answer is and that the class that leave this action invariant is those which satisfy the following algebra, the following relation, which is that the conjugation of the Laplacian gives the Laplacian itself. I'm using matrix notation here. I'm assuming that these are infinite power series of differential operators. And so, and indeed, this is one definition of the higher spin algebra. But this is work by Eastwood. So, sorry, what? So, okay, just view the Laplacian as a discretized matrix, large, and view these things as matrices. And now you ask, what are the collection of matrices that when you act with a U, discrete Laplacian U transpose, you get the Laplacian? It's a collection of matrices. Right, and so if you feed that back into the free action, right, you see that those transformations of the field leave the action invariant. Because you get phi u Laplacian u phi, that leads to phi Laplacian phi. And so these are the symmetries of a Euclidean higher spin theory if we allow for non-local transformations as well. Okay, so now I'm going to just declare to you that the Q's, well, it's also visible in the wave function, and it's why this wave function is higher spin invariant, that the Q's transform under these objects as if X was another matrix coordinate, which was rotated by this class of ux comma y's. And so now we can ask the question, of all the degrees of freedom in U of X, sorry? The Uij is an ON transformation. So that rotates the N index, because we want that to be invariant, and then the other one rotates the X index, so to speak.
You can't have a Uij.
A what?
You cannot have a Uij of x comma 1.
Here they're separate symmetries. There's image ON cross higher spin. In more complicated theories, we may have to confront that. But so far, the vector indices don't mix with the space-time indices, with the spatial indices. It's an interesting idea, though. Okay. So maybe I should call this O. Okay, so now we're going to end with a simple exercise, just to get some intuition. So imagine a discrete matrix where you have a K, one side which is K elements, and another side which is N elements. So a K by N matrix where K is much larger than N. And I'm going to give you an assignment now. And imagine that I'm allowed to rotate K and N, this matrix by K and N. What is the analog of the number of eigenvalues for this matrix? How much data does this matrix actually have if you only want to consider the invariant rotation? Any takers? So there are two possibilities, K or N, and we're in the limit where K is much greater than N. When K is equal to N, the answer is N eigenvalues. What about when K is much greater than N? K? N? Okay, who votes for K? Okay, by democracy. So the answer is N, and one way to think about it is that if you take this metric and multiply it by its transpose, you can get an N by N matrix. And so really the data has to be N, because there's no more data in this system. So just imagine the case where N is equal to 1. There you have a vector subject to rotations. All you have is the size, is the magnitude of the vector. Okay? So now, the reason I'm doing this exercise is that it's a grossly simplified version of the question we're asking over here, because here K is taken to the continuum limit. K is roughly the number of points, and the rotations are roughly these higher spin transformations. But the point is that, at least in some definition of the continuum limit, the actual data contained in our naively infinite number of operators Q of xi is order n. Because regardless of the size of k, there were only n invariant quantities because of how enormous the symmetry is. Now, what that means is that effectively, from the point of view of the Q theory, if we impose all the gauge symmetries, we can only really act with n independent degrees of freedom. That the number of degrees of freedom, we shouldn't really call them degrees of freedom because they're highly non-local, but the number of sort of objects, whatever they may be, at scribe plus, is n. But I mentioned a second ago, well,
the diffeomorphism somehow transform like the OK notations here.
they're a subgroup of that.
But isn't it important?
So we're in. So we've already in the perturbative limit. It's a little simpler to imagine. So we've used up most of our diffeomorphism in making each of these particles transverse and traceless, just like with the spin 2 particle. However, there remains a global higher spin symmetry, which is you should view as an extension of the action of the global SO4,1. That's what the OKs are when you do it in perturbation theory. Yeah, but they're just the global subgroup of, they're the subgroup of diffeomorphisms that leaves the classical saddle invariant. But in the sitter, we may have to gauge that as well. You see, just because just because I find a sitter and it has SO4,1 isometries doesn't mean that I get to build things that transform non-trivially. So, but I'd like to argue that perhaps what's being suggested over here is that the actual number of degrees of freedom in the theory is vastly reduced. And we could have only reached this conclusion by knowing the full spectrum, the full symmetry group, and having an educated proposal of what could complete the effective field theory. What could the microscopic operator algebra of the theory actually be? But what is n? In these theories, I said n was the coefficient of the action, which up to a number is roughly the de Sitter length squared in Planck units. And now we can conclude, I'll conclude with this suggestion over here, because if we go back to the end of the first lecture, we remember that there was a different perspective of de Sitter, where you viewed it from the perspective of an observer surrounded by a horizon. And we were wondering what this horizon could be, and whether the entropy of this horizon, which was the area of the horizon in Planck units, which scales like L de Sitter squared over L Planck squared, could be meaningful. And so maybe the fact that we got n degrees of freedom after all, even in a consideration of a theory on the future boundary, was something leading us back to the picture of the observer with a horizon, okay? Because this certainly doesn't scale like a local object in an extensive volume. It looks more like a system with a finite number of degrees of freedom, okay? Okay, so let's end over here, and then we can discuss indefinitely. Thank you.
What are the original highest fields in terms of what's the formula?
I can only tell you on a late time slice what the answer is. So the late time profiles are these Qs. So H, the late time profile H, are these Qs.
So in particular, the metric is that vector.
Yeah. So I'm organizing the discussion in a linearized way around, so let's ask this question for linearized quantum gravity about de Sitter, okay? So, and let's fix a partial gauge, which we're allowed to do, where the is traceless and transverse of the late time metric. The only thing that's left in the constraints, because we've used up the constraints, our wave function has satisfied those constraints, but we can write the wave function in that gauge. The only constraint that's left is that you're invariant under the de Sitter group itself. This is what's left as a constraint on your space of states. so long as you fix your gauge consistently, that's all you have left. And I'm claiming that this wave function is also invariant, so it's built out of the linearized profiles where we've already gauge fixing, is also invariant under the subgroup, which is the global higher spin transformations.
That's quite generic. The physical question, I believe you said mass here that should cause some wiggles in the metric.
Do you need, but we should first understand, I don't know the answer to your question already in the analysis in de Sitter at very late times, because everything is at space-like separations, and you've taken this proper volume limit, so I'm not sure what your wiggles will transform into. So I'd like to do the calculation first in that context. And there, I'm sure it will have a nice representation in terms of the conformal structure, and then we can talk about it. A comment about time. Good, thank you, I forgot about that. In the bulk, moving in time is related to the idea, if there is an action of Vasiliev, is related to the idea that there's some Hamiltonian, canonical Hamiltonian governing these higher spin fields, at least perturbatively. But whatever this Hamiltonian is, it's built out of both the fields and their canonical conjugate momenta. Such an operator can only be approximate from the perspective of the Q model, because the canonical momenta of the higher spin fields are only approximate notions. So any bulk Hamiltonian in this theory can be at best an approximate notion. And so one has to first discover the answer to that question and then try to see whether we can evolve back in the large N limit. It's an extremely interesting question. Any more questions?
You said that it's a finite number of degrees of freedom.
Yes.
But it's also a finite number of things.
Not at face value. But maybe it's finite enough that if you consider any finite region of space, for example, or the entanglement in that finite region of space, that is a finite quantity. Because you no longer have locality. It's easy to imagine that in any finite region of space, since the theory is soft in the UV, you're not going to get any UV divergences, and so if you have order n degrees of freedom, no UV divergences, it's imaginable that any entropy of a finite region will be actually finite in the ground state. So, you know, I'm not sure how to assess the finiteness of the Hilbert space question. Maybe it effectively is, I'm not sure.
Can you calculate the coefficient?
Not yet.
Let's thank you again.
Thank you.